Hello, my name is Devansh Gupta, and today I'll be presenting the paper CLIPTrans. This is a joint work between Boston College, BITS Pilani, Microsoft, and Harvard University. Lately, a lot of research has focused upon improving machine translation by leveraging visual information in the form of images. Images during training necessitate using them for inference. However, that presents a very restrictive scenario. More often than not, paired image text will not be available while testing. To alleviate this, a new research direction called image-free MMT was proposed, which eliminates the use of images while testing. This is how we define our setup as well. Naively, MMT can be done by embedding the image and its grounding caption and then passing it through a multimodal encoder-decoder trained for translation. However, it is not immediately clear how this will get rid of images during inference. Previous works aim to solve this by learning a hallucination network, which is used in place of the image encoder while testing. This network is trained by taking the grounded caption as an input and using the features from the image encoder as a supervisory signal. Finally, these embeddings are passed through a multimodal translation module to give the translated output text. However, this setup has certain challenges. Number one, you need to learn each individual module from scratch. To leverage the power of pre-trained models, you need a multilingual multimodal one, which currently does not exist. Existing pre-trained models come in pairs. They're either multilingual or they are multimodal with English. Popular models derived from CLIP also lack decoders, thus making them unsuitable for generative tasks. Secondly, training the hallucination model is quite difficult. It often requires calculating intractable losses and complex optimization. Now, these problems can be solved in the following manner. Instead of using a multilingual multimodal model, we can simply use independent pre-trained modules, a multilingual one and a multimodal one. However, we would still need to somehow bridge the modality gap. Is there a way to do this and eliminate training a hallucination network? Towards this end, we propose CLIPTrans. As earlier mentioned, we make use of the pre-trained multilingual MBART and the multimodal MCLIP. To bridge the modality gap, we use a lightweight mapping network that transforms the MCLIP embeddings to a discrete prefix sequence. This sequence is used to precondition the MBART decoder to the visual information. Decoding via beam search only begins once all the visual information is processed. To circumvent the training of a hallucination network, we leverage the pre-alignment of the MCLIP image and text encoders. At any given instance, we choose which one to use depending on the information we have, the image encoder while training and the text encoder during inference. CLIPTrans is trained in two stages. The first stage acts as warm-up for the MBART decoder so that it can adapt to the newly introduced image embeddings. This is done by training on an image captioning task with the MBART encoder kept frozen and fed a trivial input. This ensures that the output from the MBART encoder does not interfere with the actual captioning task. Here, the MCLIP image encoder is used. The second stage is used to fine-tune on the final translation task. To remove train test disparity, we now solely make use of the MCLIP text encoder. Throughout training, MCLIP remains frozen to ensure that the alignment between its image and text encoders is not disturbed. CLIPTrans outperforms all previous SOTAs significantly, especially on low resource languages. We also draw your attention towards the effectiveness of using pre-trained models in MMT by noting that the text-only MBART also outperforms previous SOTAs. Now, does captioning really help in the translation task? While we do have quantitative results that agree with this in the paper, we can also see this qualitatively. A CLIPTrans model trained on only image captioning is evaluated on German text in a zero-shot manner. As you can see, the gist of the German text is captured in the output English sentence. Using exact words would require conditional generation, which would be brought about by fine-tuning the MBART encoder in stage 2. We encourage you to pause the video and go through these examples as well. Now that's about it for the presentation. Thank you for listening. If you're further interested in our work, do check out our paper, website, and code by scanning the QR codes. Thanks again and have a nice day.